So we are ready for our next session that will be given by Professor Irad Ben-Gal. The name of the session is Explainable Artificial Intelligence, XAI, and Predictive Information Approaches for Industrial Applications. Professor Irad Ben-Gal is professor and head laboratory of AI, ML, Business and Data Analytics, in short, LAMBDA, at the Tel Aviv University. Professor, if you're here, this is the time to take the stage.
Thank you, Melanie. Thank you very much. So it's a pleasure to be here, and for the first time, the AI Week is happening in Tel Aviv University. I want to congratulate the organizers and thanking them for making it such a successful first event. Well, I'll be talking about Explainable AI and then about a specific model that deals with Explainable AI in between two time series under what we call sparse pattern condition, meaning that only part of one time series actually affect the other, which happens quite a lot in real life. So basically, I'll give an introduction about Explainable AI that became a very relevant topic recently. We'll talk a little bit about the popular approaches for XAI, and then I'll go dig into time series and the relation between them and how you can find some explainability in one time series about the other and some conclusions. So the first part is more qualitative, and I used some of the slides from KDD 2019, and the second one is more technical and based on joint work with Yuval, my PhD student. So whoever is looking for the technical equations will have to wait, and eventually I'll try to make it such that everybody are unsatisfied in the same amount. Okay, so why do we need Explainable AI? Quite obvious. Imagine a physician that gets some output from an AI system that analyzes epilepsy detection model in brain MRI data, and there is an 85% confidence of that patient having this disease. It's not enough. I mean, the physician will have a hard time to understand why this diagnosis was actually made and whether or not he or she can trust this prediction. Same happen, of course, in many other aspects. So again, imagine an example of a loan model with financial records about a person that wants to apply for a loan, and the decision is that he is not eligible. Decision by this complex AI model. And now the person wants to ask why he was denied. And actually, this is a very relevant question because it has a lot of legal consequences. In fact, if you look at recent headlines in many newspapers, you find a lot of examples where Explainable AI is missing, and this is a result of that. So, for example, the scandal with Cambridge Analytics and Facebook, or the failure of Uber or other autonomous cars that remain unexplainable. Some employment cases where there was discrimination against women or depending on age. So all these cases are actually representing business risk due to lack of explainability. And when you consider the different laws and regulation against discrimination on the basis of race, sex, citizenship, age, disability status, you realize that all those decisions that are made are quite risky when an AI system actually generates them, and you don't have a good explanation why you got a certain output. And this is why, for example, in the GDPR, besides measure of fairness and transparency and privacy, there is a whole chapter dealing with explainability. So it became a regulation to any business, and any of the business that will use AI will have to deal with explainability. And it's not simple, because when you talk about explainability, different people in the organization would like a different explanation. So you can talk about a business owner that have to trust the decision and is not sure about it, or the customer support that has to answer a customer complaint and needs to understand from the model what is the best answer. Or if you talk about IT, how he or she should monitor or debug a model. Or if you talk about the data scientist, maybe some explanation how we can improve the model. So there are many different explanations, and it's not clear what are those black boxes providing and how they should be interpreted. And the idea that actually was supported by DARPA is to, beside creating or supporting all those AI models, most of them nowadays, most of them are black boxes, to provide also a sort of an explainable surrogate modeling. It can be a local or a global, we'll talk about it, that besides providing just a decision, will provide also an explanation. So the user eventually is getting not only a recommendation, but some notion and insights about why the system has been decided to follow a certain decision. And an input can be then brought back to the system to improve it. So explainable AI is not only that people learn from the AI system, but vice versa, also the AI system learning from human experts. And there are many good examples nowadays of explainable AI. You see this is an explanation model of NVIDIA PilotNet for autonomous vehicle, trying to explain which are the pixels or the parts in the image that actually affect the turning of the steering wheel. And once you understand it, for example, you can see if edges are missed, or if there are problems in the identification of obstacles, and you can actually improve the model that way. This is a very famous picture of explainable AI when actually presented in 2016 by Irad, where a husky was classified as a wolf, and when they ran the explainable AI system, what they found that the pixels that explain this type of misclassification are actually, many of them, related to the fact that there is snow around this husky. And in the training database, of course, there were many pictures of wolves that were running in the snow or in a snowy environment. So the system recognized it as a feature of a wolf. And of course, once you understand that, you can recalibrate the model. And without having this insight, the data science could actually focus in a wrong type of modeling without understanding why there is a misclassification. And there are many types of XAI, of explainable AI system. Some of them try to focus on explaining the entire model. Some of them are more local, try to explain case-by-case example or local decisions. So the first one are better for better modeling decision, while in most cases the local XAI is better for debugging or for some interface with the user that has to understand on a case-by-case basis why a decision was made in that specific case. In both types of XAI, what we find in many cases what we call the surrogate modeling. It's not a new concept. We know it from statistic design of experiment for many years. And the idea is simple. While you have your black box trained on the data, you have also a surrogate model that is more explainable and more interpretable. And what you try with this simple model, sometimes locally, is to actually predict the output of the black box model, again, even locally. And if you are able to do that successfully enough, in many cases, this simple model can help you understand how, for example, each feature contributes to a local decision. So I'll give you an example. This is the local interpretable model agnostic explanation LIME, again, from KDD 2016. And what you see here is what you see here is a complex decision space. However, in a certain local area, you can actually approximate quite well the decision based on a simple linear model to distinguish between the cases, the red cross and the blue dots. And the example there is, the case was to predict a household with a yearly income of above $50,000, and you could find very local specific rule for this type of population that they can predict very well whether or not the yearly income is above $50,000 with very local and simple rules that can be totally understood. Sorry. And it can even be represented by if-then rules. And I think that the main explanation was that if you are married, you are getting more than $50,000, so all the bachelors should run and get married. So this was the LIME. And when you apply it to more complex problem, this is another problem where you try to identify a tree frog. And what you do a perturbation of local pixels, and then you run it in the model, and you find what is the probability that it will be identified as pixel belonging to a frog. And then you actually take all those inputs and you combine it locally to, I think it was a nonlinear kernel model. You find exactly those pixels that explain well why this specific picture is actually classified as a tree frog. So it works also well in image. And if you move to more global type of explainable AI, like the Shapley additive explanation value, what it does is, again, the concept comes from collaborative game theory when you try to find the contribution of different players to a collaborative game. It was applied, I think, in 2009 2009. It was applied to find the contribution of different features. So now the players are features, and what you try to find is the contribution of a feature to the decision of the AI system. And what you try to do is to see how each feature can change the expected model prediction that when conditioning on that specific feature. So, for example, here you have a score prediction or a score result of an AI system that on average is around 24.41, and you have those different features that can either shift the value towards lower values or higher values, and to each of those features you can actually apply the Shapley additive explanation value and find exactly how they affect the total score. So basically you end up with a good understanding of the marginal contribution of each of those features. And the mathematics, again, is not complicated. What you do when you have a set of F feature, you select each time a subset of S features without having this feature I that you want to measure. And over all the permutation of S over F, you find, according to the model that you are trying to analyze, what will be the output of the AI system when you have this subset S, including that feature, with respect to the same function when you just have the subset S without having a specific value of I. So basically you are looking for, again, for the marginal contribution of this ith feature to see how it changes the value, and eventually you can contribute to each feature this importance value. So in one hand it is quite simple, on the other, and actually follows a certain or actually obeys certain axiomatic condition, which is good. On the other hand, you see that whenever you need to analyze the contribution of each feature, you have to select all the different subsets that do not include this feature. And this is a very tedious and computationally expensive process, even when you are just considering a single model, a specific model, let alone if you want now to find the contribution of a feature over a subset of different models. So it's a simple idea. It works well, but it has some disadvantages and challenges that you need to follow. And it works quite well again when you apply it. This is a SHAP value applied to text when you want to find the important words that will help you to classify this text, or you want to analyze a very simple interaction between two features. One of them is the sex and one of them is the age, how they contribute to some kind of a classification model, or when you have an image recognition, so they work well. But again, as I mentioned, there are a lot of limitation of those models. So there is no one learning technique that optimizes both the model and its explainability. And in fact, what we see usually is that models that are very accurate are less explainable, while models like classification rule and decision tree that are very much interpretable are poor in terms of their accuracy. So this is a gap that needs to be answered. SHAP assumes feature independence in a way, so it can actually analyze interactions up to a second. I even didn't see a third order interaction. Although we know that in reality this is not the case. Even in a simple picture, there is an interaction between pixels, and definitely in business problems, it's not enough to know the income of the person and for example, some demographic area where he lives. There is a lot of information hidden in high-order interactions, and this is something that the current SHAP models are poor in explaining, exactly these high-order features. And the fact, again, that usually you have to have a model in mind in order to find the contribution of each feature, but in many cases, you are not sure whether this is the right model, whether other people will use that model, and so on. So it's a model independent. So having all those limitations or challenges in mind, what we wanted to try to do, and this is the second part of the research, is to apply a sort of an explainable AI for problems that actually contain a lot of interactions of high order, and at the same time they are sparse. So we focused on time series analysis where, in fact, one time series can affect the result of another time series, okay? And when you look at real problems, you see that in many cases only part of those time series of the possible values of one time series are actually affecting the other. So it's a sparse condition. And you can find it, in, for example, in financial time series where, the value of one stock actually affect another. You can find it in, these are weather maps, where 100 of, time series weather parameters in one region can affect, the weather condition in another region. You can find it, of course, in cyber, when you look at zero-day attack, where only a combination of part of the time series can indicate that there is an anomaly. You can find it in neuron activities in the brain, when only part of the activities actually affect other time series in other part of the brain. So it's very common to have this situation of what we call sparse information condition, and to apply a Shapley value importance calculation over all the time lags and over all those different time series. It's simply something that cannot be done in an efficient way. And when you talk about something that is, you want to separate it from a specific model assumption, you go back to Shannon. You go back to Shannon, talking about the mutual information between two variables, and they can be also two vectors of variables. And as we know, they are model independent. What we are looking is just the distribution of one random variable depending on the other. So in fact, it can be actually well approximated by the difference between the joint probability of those two variables with respect to the multiplication of the marginal probabilities of those two variables. And of course, if they are independent, the mutual information will be zero, or the Kullback-Leibler distance will be zero. And if not, it means that they hold one random variable, or one random vector holds information about the other, independent of the model that you want to apply. And this is exactly what we want to do, because in many cases, if we know a priori which part of a time series affect the other, which features are important, we can actually fit a better model to that problem. So it's a useful approach practically when you know the type of dependencies. Having that in mind, exactly those simple mutual information relation, what you try to do when you talk about two time series, one is denoted by X, with respect to the past. This is the past of one time series. So you have this tau P representing the past of p previous values in one time series, and you want to find information about the future of another time series. By the way, a specific case would be that x and y are equal, but in general you can talk about a different time series, and you want to find how the past of one time series actually contain information about the future of another time series. And this is called past-future mutual information. It is related to many, many different types of information measure that people are using, sometimes in different society without knowing that the same name is used for different tasks. But you can find people that, a lot of literature that is talking about predictive information, directed information, transfer entropy, and so on. I won't go into that, we don't have time, but people are busy in finding those features because they understand that they are measured, because they understand those measures are important. And when they try to find practically those information measured between two time series, they either use a sort of a straightforward estimation approach when you look at a two-time series over a space and you divide it to bins, or they are using different type of clustering. The most common is the K and N, to find how these time series are related to each other and exactly where in the space one time series is affecting the other one. And it turns out that although those models are okay in low order, they have a lot of problem when you want to deal with long time lags. And specifically when you have these long time lags, when only part of the past actually affect the future of the other time series. And this is what we call the sparse information condition. So not only that you have a very long dimension, but only part of it is relevant. And then what we did, we applied a method that is used for compression, to compress two time series. I don't have time to go in deeply into that, but basically one time series is represented by those nodes. It represents the conditional value of the y time series, the output time series, given a context that is represented by those branches. So in each case you can find exactly how the output is affected by a specific context. And the nice thing about this model that it trims out all the irrelevant contexts. That you are left only with relevant type of context. And what we did, we also applied it to real data, for example, financial time series, and got a complicated model that explain, I will go over it in a moment, that explain how, what type of relation exists between these two time series. And basically what we do, we apply the simple algorithm. Once we have this compression way to find the relation between two time series, what we do, we always look for, it's a simple gradient descent algorithm. We look how much we need to increase the context in order to find new information. Or if you want, we can actually start with a very long time series and trim it to see if after a certain point we start to lose information. And in many cases, when we see that there is some kind of stability, we know that this is an optimal point that represents the optimal context. Instead of looking at, I'll just say that when we do experimental result, we see that this type of method, even when you increase the alphabet size or you increase the sparsity of the problem, you don't pay a lot of price. This is the error of the real past-future mutual information, depending on the sparsity of the problem. And you see that these type of models are very robust, while the other are less robust. And when you look, this is an analysis of time series of bank index 7 or 8 banks in US and Europe, and you see and what we try to find is how the index of one bank affect the other. And what you see is that you start with a very long time series, a lot of sequence, and you start to trim it, and you are not losing a lot of information. However, at a certain point, when you reach exactly the optimization point where you start to trim features or patterns in the time series that are important for the prediction of the other, you see a very sharp decrease in the information. So this is a very good way following that algorithm to go, and as long as you don't see a sharp decrease, you can actually decrease the context size up to a moment that you know that if you increase more, you lose information. And you are ending up with the exact amount of patterns under those sparse conditions that you can use for predictability and explainability. And this is, for example, the effect of the HSBC on Deutsche Bank, two different banks. And I don't have time to go into the interpretation, but what you see is that there is a symmetry here between the banks, meaning that the market is efficient. There are some higher stability lags. In this case, we took each 10 seconds the value of the stock, and what you see is that after a certain stability region, you have a much higher probability to remain stable. So it's something that can help you understand the behavior of those different time series. And I don't have, I'm out of time. Whoops. And it doesn't work. Let's see. So I would just say that I don't have time to show it, but this type of trimming is very relevant also to the information bottleneck work of Slonim and Tishby. I think that both of them were here yesterday at least, and to a deterministic version of it. So we can see the same behavior when you apply the information bottleneck, meaning that you can use those type of compression models to squeeze information about the important patterns and to increase explainability. And the last slide is just to show you a very recent set of works that actually use complex neural networks to find in a more accurate way the different type of mutual information measure. So, in one hand, those complex network create a lot of ambiguity and fuzziness because they are not clear. But at the same time, you can use the same type of models to actually try to estimate exactly those information measure and find with those models the explanation that actually was created by the same models that starting with. So basically the conclusion is that XAI is certainly an important and emerging area. There are crucial challenges in XAI. All those issues of high complex patterns are very initial in the current method. We proposed one method to deal with a specific scenario of relation between time series under sparse information condition that works quite well. And it is related also to other aspects that now people are using also to explain deep networks. This is the work of Tali. I think that you saw it yesterday. And the nice thing is that those models can also be used to explain better the ability. And future of AI is this? Does your car have any idea why my car was pulled it over? So, you know, eventually everything will be explained somehow by those machines. I want to thank specifically Yuval and Aviv. This is a LAMBDA lab, and you are welcome to look at the website. We promote collaboration with different companies working on real data. Thank you very much.